I'm representing the second set of results, and you can see after Joachim, you already know, we have topics, so I'm topic 2, and we're looking into the future, and we want to understand what the report tells us about the future. So, future changes, risks, and impacts. The overall key message, and you may remember that, but it doesn't hurt to repeat it again, is the following. Continued emission of greenhouse gases will cause further warming and long-lasting changes in all components of the capital system, increasing the likelihood of severe, pervasive, and irreversible impacts for people and ecosystems. That's the strongest message we have heard coming out of the IPCC, and that's really something to remember. The second set here is equally important. What we actually have to do. Limiting capitalism would require substantial and sustained reductions in greenhouse gas emissions, which together with adaptation, they have to go hand in hand, can limit capitalism risks. So that's the overarching message from our topic on what we know about the future. And I would like to invite you to go with me step by step now to understand the individual parts in here. What can we actually say about capitalism projections? And I'm not a modeler, but I find it incredibly interesting to learn from my colleagues here, and I'll try to convey that in a way that also makes sense to you. So the way we think about projections, of course, is based on scenarios. Scenarios of future projections, also one of the headline statements, of greenhouse gas emissions, they vary over a wide range depending both on the socioeconomic development that will happen and future capital policy. So we cannot possibly just have one scenario. It really depends on how our world is going to develop and evolve. What we can say, and that's important, is that cumulative emissions of CO2 largely determine global mean surface warming by the late 21st century and beyond. So it's all about these cumulative emissions, and I'll show you how that plays out graphically. So let's take a look at one of these graphics you have seen earlier, and let me just explain a little bit what is behind, because not all of us are really experts in here. So what you see is a really elegant, I think, combination of the scenarios that are used in Working Group 1 and Working Group 3. So the one you have heard Pachi talk about, these RCPs, these representative concentration pathways, there are 4 of them. And the reason there are only 4 is because they're incredibly complex on the biophysical side, on the physical side, biogeochemical cycles, but also the carbon energy balance, enormously complex. And I was intrigued to hear that it takes actually a couple of months to run one scenario for just 1 century. Okay? So 4 of them. And as we have heard earlier, they represent radiative forcing, one of these really technical terms that we non-techies find difficult. So what it actually means is the amount of change a certain driver, let's say greenhouse gases, force on the energy balance of our planet. That force. And it's smallest in this RCP we call RCP 2.6, and it's highest in the one that we call RCP 8.5. So what you see here, and let me see if I can pull that up, are 4 lines, and you can see the 4 colors below. The RCP 2.6 is the one we kind of like best, because that's the one that has most stringent mitigation included. The 2 middle ones are stabilization scenarios, and the one you see in red, obviously, is the one that has high emissions, right? So that's not too difficult to understand, I think, right? So what we see in black is observed emissions, historic emissions, and then you can see these 4 scenarios, and you can see how they diverge more and more towards the end of the century. Now, what's interesting, I find, is that Working Group 3 used a slightly different approach, and these are the scenarios you see listed at the very top here. And they're measured in CO2 equivalents and expressed in ppm. And many of you have heard about the 450 ppm we like to achieve, right? So the 2-degree target is an important one, and it roughly corresponds to 250 ppm. And you can see, despite some slight variations in the way these scenarios are run and based, they nonetheless quite nicely overlap. And so you can see how many or how much emission greenhouse gigatons of CO2 per year we would have according to these scenarios. Now, what's important is what that means for temperature. And there was an earlier question here after Pachi, and I think I can come back to it. So this graphic shows cumulative emissions. So these are all the emissions that have accumulated since industrial times. And we see that at the bottom, two slightly different units here, one in gigatons of carbon, the other one in gigatons of CO2. Doesn't really matter. And you see on the y-axis temperature relative to pre-industrial times. Now, if I include a rough 2-degree target here, and we get roughly into that middle area between 430, 480 and 480, 530, which is roughly our 450 target, we see that we end up with cumulative emissions around 2,900 gigatons CO2, which is equivalent to 790 that we have heard earlier, right? That's our carbon balance. Think about a carbon balance. Think about it as you would think about a landfill, right? We can dump stuff into a landfill until it's full. And so we have already filled up our landfill with CO2 emissions 2/3 of the way. So we have 1/3 left. So what do we do actually when we keep filling it up? Well, what we do is we just accumulate more and more emissions, and it's more and more difficult, impossible actually, to reach our 450 target. So what we see here in the plume, in this orange plume, is all the scenarios we have, and these ellipses correspond to the ppm targets. And the further we increase our emissions, the higher our ppm gets and the higher our temperature, right? That's what this graph shows. Now, what do these projected changes, according to all scenarios, mean for our capital system? There are 4 messages here you should remember. Surface temperature, irrespective of the scenario, is projected to rise over the 21st century. Doesn't matter which one will follow, temperature will rise. It's very likely that heat waves will occur more often and last longer, and extreme precipitation events will become more intense and frequent in many regions of our planet. The ocean will continue to warm, and global mean sea level will rise or continue to rise. So let me show the graphics that go with that. The first one has to do with temperature change, and what you will see in the series of graphics is we use the 2 scenarios, the best if you want, and the worst case scenario, the 2.6 and the 8.5. All again for the 21st century. You see temperature increase compared to the most recent time period, our baseline, 86 to 2005. And what you should notice is that, for the next 30 years or so, it doesn't really matter so much which scenario we follow, but after that point, the temperature increase varies dramatically. So it matters which scenario we follow, what policies we adopt. And temperature increase, if we go all the way up, so the uncertainty, the shaded area around the red line, would get us up to 4.8 degrees warmer than now, roughly. And that's tremendous. For sea level rise, similar interpretation for the graphic. You see the 2 RCPs, blue and red, and in both cases, sea level will continue to rise under the worst case scenario, probably up to 0.85 meters, and that also is tremendous. Now, what topic 2 has done, and I think that's really important, is that it stresses that impacts and future risks are not evenly distributed. So here, I'm a geographer, here we have a map that shows clearly the regional differences with respect to temperature change and sea level, and precipitation. Sea level comes next. On the left-hand side, we have the RCP 2.6, our best-case scenario, stringent mitigation. On the right-hand side, we have our worst-case scenario, RCP 8.5. And you can clearly see that some areas, both over the ocean and over land masses, will warm much more than others. And so the largest increase in temperature we can definitely see in the tropics and subtropical areas. I'm not sure if you can see it, but there are dots on that upper map. Yes, you can. So the dots, what do these mean? We call it stippling. It means that most of the models agree on the change, most of the models 90%, and they distinguish quite nicely between natural variability and actual change. So the more dots you see on the temperature, you see many dots, we know that this is pretty much what we're going to face in the future. Precipitation is not so easy. So you can see many more lines here, which means that the models don't agree so much, and it's not so easy to differentiate between natural variability and change. Under a 2.6 future, we may not see a whole lot of differences in precipitation, but we certainly would see those pronounced under a high emission scenario. And what you see is that more precipitation would be expected in the tropics, but also in the high latitude areas. The mid-latitudes are a little tricky, so for us here, what we do know is that wet areas, areas that are already wet, will become wetter, and areas that are already dry will become drier. In terms of ocean temperature, I should say, do know, it's the upper one, oceans will continue to warm. You can see that in both scenarios. We haven't talked about ocean acidification, but do know this is one of the important results. Ocean acidification is occurring. It will continue to occur. What it means is a decrease in pH, which has significant implications for marine life, of course. Sea level rise, this is what we can say here. Again, much more dramatic under the 8.5 scenario. We can also say that the rate will be higher, and I did not know that, but I learned. Sea level is also not homogeneous. There are areas that will be more affected than others. Risks and impacts. So what do these changes mean for ecosystems and people? You've heard that first sentence. Climate change will amplify existing risks and create new risks for natural and human systems. And just as well as the natural changes, risks will be unevenly distributed, and people who are more disadvantaged, people and communities will face higher risks. There's absolutely no doubt. Now let me explain a little bit how risk is conceptualized in the fifth assessment report. And that comes out strongly from Working Group 2. Risk, we normally understand in our community as the potential for harm, even though the outcome is uncertain, or the potential to lose something which is really of value to us, right? That's risk. And we understand risk in Working Group 2 as an outcome of hazards, climatic hazards or shifting trends, exposure, people, ecosystems being in areas that are likely to be affected, and vulnerability. And for those of you who have followed the IPCC for a while, you probably have noticed a slight change in the definition of vulnerability. That's important. What we understand now under vulnerability is a propensity and predisposition to experience harm or to be adversely affected. And vulnerability, as we understand it now, exists in every society, independent of a hazard. Poverty is an incredibly important and devastating driver of vulnerability, and that is captured in this understanding. Vulnerability, of course, also includes limited adaptive capacity and the ability or the inability to absorb a couple of shocks that happen back to back. So this is a little summary for those of you who have followed. In the AR4, we understood vulnerability as the result of sensitivity, exposure, and adaptive capacity, but it was always linked to the driver. And now we have decoupled it from the capital driver, acknowledging vulnerability, as I said, in every society. That allows us to put much more emphasis on inequalities that drive vulnerability in societies. And we have spent quite some time in our chapter, Livelihoods and Poverty, but also in the technical summary, to highlight what inequality really is. And what we can say with confidence is that inequality is driven by dimensions of disadvantage along the dimensions or axes of gender, race, class, ethnicity, ability. And the more disadvantaged people are in their society, the more marginalized they are, the more vulnerability they face. whereas people who are more privileged have higher resilience, face lower vulnerability, have higher capacity to adapt. That's a new aspect in the assessment, and from a social science perspective, I would say it's revolutionary. This table now, if you want, is at the core of future risks. And it builds on what Joachim had already shown you. It uses the same icons, but now it looks into the future. And let me zoom in, just like Joachim did, because this is too much to grasp. We have the same key risks for sectors, physical systems, biological systems, human-managed systems. But then we use something that you haven't seen yet. And here, I would say you just have to trust us. Trust me. I'm credible, right? So what we do here is we don't use projections. We don't use scenarios. There aren't any scenarios that project inequalities over the next 80 years. We use our best judgment. We call it expert judgment, based on the literature we have reviewed, summarized, based on our understanding of different regional dynamics. And we present these risks for the present. You can see 4 horizontal bars, the present, the near term, and 2 future scenarios, long term, one that represents a 2-degree target and the other one that represents a 4-degree target, again, building on the RCPs. The wider, the longer, if you want, that orange bar goes to the right, the higher the risks. And then you can see that orange-white striped area. That's adaptation. We can reduce risk through adaptation. And even if the risks are high, the potential to reduce it through adaptation is what we are interested in. Let me zoom in on Europe. Here are examples. These are not the only risks. But what you can see, and that's consistent across all regions, is that risks increase with further warming. There's no doubt. Here are the examples. I show you 2 more, one for Africa, one for the ocean. Do note that for the ocean, the specific example is coral bleaching. It's a solid orange bar into the long term. There is essentially no potential for adaptation to save coral reefs under 2 or 4 degrees further out into the century. So we are interested in limits to adaptation, and this is a way you see them represented. Quickly, some words about fisheries. So that's a graphic that is built on a simulation. It's a medium to high emission scenario that is underneath here that shows how catch potential for marine fish and small invertebrates will change. The yellow and orange and red show decreases, and you can see where they're going to happen. Again, not evenly distributed. The regions most affected will be around the tropics, around the equator, and the high latitudes. And I work in Senegal, for example. What that means for Senegalese fishermen is detrimental. Impacts for food security, you've seen that graphic. Let me explain it a little more. What we see here is a summary, a really nice synthesis of a number of studies that have summarized projections for major crops, wheat, rice, maize, and soy. And what we see very clearly is that losses in crop yields, so the orange and brown ones, will increase the further we move out in the 21st century. And also the intensity of these losses, darker and darker and darker colors, show the increasing risk for people and food security. And these results are really, really strong. Reasons for concern, I'm going to introduce those. My colleague Leon will talk about them a little bit more specifically. These reasons for concern, I'm sure you have seen those. It's the famous burning ambers graphic, right? How many of you have seen those? How many of you have seen the color purple in them? Uh-huh. We now have reached color purple, meaning these burning ambers show summary risks for 5 major areas, and you see them written at the very bottom. It's for the first time that we have reached a level of risk that is beyond what we had in previous reports and hence needed a new color, purple. Again, risks increase with further warming, and they are highest for unique and threatened systems, including coral reefs, but also unique human systems, people living in the Arctic, people living in high mountain areas. Change beyond 2100, what can we say? Many aspects of
no tool
and associated impacts will continue for centuries, even if anthropogenic emissions of greenhouse gases are stopped. So even if we manage to stop them now, the effects will linger in the system. And the risk of abrupt and irreversible changes also increases with the magnitude of warming. Two quick examples. For temperature, you can see the RCPs again, all four. Even if we stopped them, if we stopped emissions before 2100, temperature would continue to increase, and strongest on the RCP 8.5. For sea level rise, even though the models probably could benefit from more research, what we do know is if we lose the Arctic ice sheet, abrupt sea level rise is most likely the consequence. And that's what you see in the high gray bars, up to 7 meters, assuming the ice sheet in the Arctic goes. Here's my key message again. To remember that a fantastic collaboration of scientists with really important results. They're all a little scary, but I have 2 more colleagues who will show us a positive way. Thank you.